Welcome to this presentation on geophysical investigations for dam safety. Geophysical methods are used for rapid and cost-effective investigations and monitoring of dams. This has been brought to you by AF Academy. AF Academy provides training and knowledge sharing platform to decision and policymakers, working professionals, operating level personnel, and aspiring students willing to specialize in technical sectors through mediums of training and courses. This is a glimpse of the training programs which we have conducted in the past. This is one of the dam safety programs we conducted. Other topics include subsurface utility engineering, rapid and cost-effective site investigation for engineering projects, for monitoring of dams, hydropower projects cost-effective solutions, GIS field data collection and reports, detection of leakages from pipelines and treacherous rehabilitation, ground penetrating radar, including advanced 3D processing. This presentation is being brought to you by with Parson, the technology partner of this. Parson is the only company in India providing complete dam geophysical solutions, having experience of more than 50 dam investigations. The main strength is the highly experienced and trained staff. It has offices in Delhi, Bhopal and Kolkata, and Bahrain and Saudi Arabia. The company has work experience in more than 14 countries around the world. A brief introduction about myself. I am Sanjay Rana. I'm a professional geophysicist with 30 years of work experience. I am chairman of AF Academy and managing director of Parson, which is an engineering geophysics company. I graduated from University of Roorkee, which is now IIT Roorkee, in 1990 in applied geophysics. I'm also a member of various working committee for development of code of practices and standards, including IRC, Indian Road Congress. Dam geophysics was pioneered by me in 1998. That was the time when I conducted the first geophysical investigation of a dam in India. Apart from that, I have also integrated geophysical approach for investigation across flowing rivers for dam safety, completed geophysical investigations of 72 hydropower projects till now, and I have extensive experience of geophysical investigation of dams of all types, that is concrete, masonry and earthen. More than 80 dams have been investigated by me till date. I'm also the principal author of guidelines on geophysical investigations of dams. Now coming to the topic of the day, in the famous quote of Sri Visvesvaraya, the engineer's first problem in any design situation is to discover what the problem really is. What the problem really is. Now today, we are trying to solve our problem, we are trying to accomplish our goals, but if there is someone offering us tools, saying that tools are available, use them, don't be scared, your job is still safe, we say no thanks, we are too busy. So most of us are too busy to improve. That is the situation we are into. And it's about adoption of new technology, adoption of new techniques into our projects. And this particular presentation is going to deal with one particular technology, and that is of geophysics. So once we talk about geophysical investigations, I always love to start with this particular slide, which of course is not geophysical, it's all medical imaging. So you can see ultrasound, you can see X-ray, you can see MRI, CT scan, etc. Now what are we doing here? We are basically sending different kind of rays and waves inside the human body to create the structure of what is inside it. Internal structure of the human body we are trying to reconstruct by sending different kind of rays and waves. We are not cutting open the body, but we are doing it in completely non-destructive manner. Now compare these images with these images of geophysical investigation. Here is a dam, it's a concrete dam. Here are the fracture zones. Another dam, masonry dam, the weak zone here, or the low density zone here. Similarly, a complete dam from one end to the other around 450 meters, and all the weak zones have been brought out in this particular image. So it's always good to understand geophysics by comparing with medical imaging. That is, just like in medical imaging, in a non-destructive manner, we are trying to create image of what is inside the human body. Same thing we are trying to do in geophysics about subsurface. Of course, there is a major difference between the two in the sense that job of a geophysicist is much more difficult than a medical imaging professional because there is something called normal in human body. For example, these are joints, so they will not be interpreted as fractures. If there was another one here, it would have been interpreted as fracture. But in case of Earth, well, there is no normal Earth. Earth changes from point to point. That's number one, limitation number one. So interpretation of geophysical data is much more complex. Secondly, human body is available for investigation in 360-degree. For example, this person goes inside the tunnel and transmitter and receivers are working in 360-degree, and that way the image is being created. Unfortunately, in case of Earth or materials like dams, we are having access to only one surface, and that is the top of the Earth, and that is why again the job becomes little more difficult. Nevertheless, it is the best comparison to start with. As a science, when we look at geophysics, it falls at the intersection of geology, physics, and maths and computer science. So this is where geophysics comes. Now, why use geophysics? So the first answer is that it's again going to the medical imaging thing. Why go for an X-ray or ultrasound? Because you do not want to cut open the body. You do not want to do destructive testing, and you always prefer non-destructive testing because the cost is low. So in geophysics, the cost is low. It covers large areas in a very quick manner. It gives continuous information. Look at a situation here. This is a limestone pinnacle. There are other objects here. There is a void here. There are other objects in the subsurface. If you're doing drilling, you get just the discrete information of one point where you're doing the drilling. Whereas once you do a geophysical investigation, you get continuous information. So you do not miss on anything which is in the subsurface. Optimization of drill holes. Once I say this, please don't take home the message that you do not need drill holes if you do a geophysical campaign. The idea of a geophysical campaign is to get a continuous image and then optimize your hole only at the place where some anomaly has been detected. And of course, it leads to minimization of surprises. It's always good for early stage application. More often than not, it is being used as a firefighting tool. That's not a great idea. It is good for early stage application for better planning and smooth execution. Choice of the method, the geophysical method which you are going to choose for your work is as important as whether you do geophysics or not. Because choosing a wrong method can always result in failure of the project. So the factors which you consider is what type and shape of feature is being imaged, what are the physical properties that will show the best contrast, are there any strong but irrelevant contrasts that will mask the result, to what depth must the survey penetrate, what is the spatial resolution required, what is the time and cost constraint, are there any spatial restrictions, that is access or damage. All these factors have to be considered before you decide which method should be used for your work. Now coming to advantages and limitations of geophysics. Advantages, as we saw earlier also, it's a rapid and cheap survey tool, easily integrated with other forms of ground survey, for example your drilling data, your visual observation data, etc. It's non-destructive. So it's very useful for archaeology, dams, urban areas, etc. Modern processing methods give a visual image of the subsurface. You are practically able to see the whole thing almost in 3 dimensions. Limitations, of course, are there, that it can be ambiguous without controls. That is, geophysical data cannot be interpreted unless you have controls on your data. We'll look at this particular aspect as we go further in the presentation. It has poor discrimination in some cases. That is, as you go deeper and deeper, the resolution is becoming lesser and lesser. And it can suffer from noise or artifacts. Again, it depends on the way you are acquiring the data, the way you're processing the data, and your site conditions. Now there are different methods for different properties, so it's important to understand what property we are interested in. For example, you want to find out the strength of the formation, seismic methods, because they measure elastic wave velocity. You want to find out buried objects based on the reflection, etc., ground penetrating radar working on EM pulse velocity. We want to find out things like saturation, water saturation, which will ultimately change the resistivity of the soil, DC resistivity methods. EM conductivity methods, again measuring the same thing, resistivity or the reciprocal conductivity. We want to find out the materials which have some magnetic property, magnetic methods. We want to find out the objects having a contrast in the density, for example, a very dense material or a void underneath, gravity method. So the value of the subsurface measurement is determined by the contrast in the relevant property and hence the material type, and by the three-dimensional structure of the object. Return on investment of geophysics is huge because it gives you detailed investigation of site, saving huge cost towards change plans, project delays when surprises crop up, node drilling and node digging, vast information at fraction of cost of traditional methods, but it's for early stage application, for better planning and smooth execution. Now let's look at the topic of dam investigations. Present scenario of dam investigation can better be termed as dam inspections. That is, mostly it is based on surface only observations. These are extremely dependent on the inspector who is doing it. His level of motivation, his involvement in the job, his level of knowledge, experience, everything counts. And there are very few or almost no standards which are widely popular for these kind of inspections. So what we are doing at present is we have very little data and a lot of assumptions and opinions whenever we are forming a plan for dam rehabilitation. If we look at a machine maintenance approach, reactive is fixed when the equipment is down, periodic is scheduled maintenance, proactive is eliminate defects at an early stage, and predictive is use analytics to predict machine failures. In case of dams, we are mostly at the reactive stage or at best at the periodic stage. We are not in the proactive or predictive stage. When we talk about preventive maintenance, again taking the example from machine preventive maintenance approach, it basically involves various operations like replace worn components, clean and restore components, avoid the consequences of component or system failure, improve reliability, train experts on proper procedures and techniques, etc. etc. Idea is that we should be able to do things before something goes wrong. So the proposed approach which we are talking about today is having more data as a result of investigation so that less assumptions and opinions are there in our approach. So importance of timely detection. Let's have a small look at this video which gives the importance of timely detection of problems, especially in cases of dams.
Most all dams experience seepage to one degree or another. While the dam experiencing seepage may appear in sound condition, there may be damage occurring to the internal structure of the dam. If seepage flow rates appear to be increasing and the flow is not clear and is carrying material, internal erosion or piping is likely occurring. Piping is an erosion process that occurs inside the dam whenever the seepage flow starts eroding embankment materials out of and away from the dam. This starts at the downstream slope or toe and moves rapidly upstream to the impoundment. This process will tend to accelerate as the expanding larger opening or pipe allows for increased seepage flows. If left unattended, the seepage flow and progressive internal erosion will soon get out of control. When the internal pipe or void becomes large enough, the embankment structure above it will collapse. This will result in a failure of the dam's embankment and a potentially catastrophic release of the stored water, which may cause serious property damage and loss of life.
So what is the solution? As we have very clearly seen that there might be defects before even you see manifestation of these defects. So what is the solution? Solution is timely detection. Detection before the problem gets out of control and becomes so big that it cannot be controlled anymore. And how do we do that? And that is where dam geophysics comes in picture. So why geophysics for dams is so important? Because it's the most suitable method for regular health checks of dams, for early detection of problems. It's totally non-destructive, so extremely suitable for a structure like dams. Helps design rehabilitation programs better and accurately because now you have more data to make your plan based on rather than just having assumptions and opinions. helps assess success of rehabilitation measures undertaken. Sometimes we put a lot of grout inside the dam, but we really do not know whether it has cured what we wanted to cure. Identification of damaged areas inside the dam body, identification of not visible fractures and voids, and identification of zones of seepages. So basically a lot of information at low cost and in a very less time. The available solutions, if you just look at this table, I'm not going to read through this table, just point of showing this table is that whether it is a concrete dam, whether it is earth embankment, whether it is masonry, and whatever is the problem, be cracks, degradation, water leaks, landslides, sinkholes, water leaks, strength, whatever it is, there is one or the other method which exists to address to this, the particular problem we are talking about or the issues and concern we have. Now, the most important part is which technique or tool we are going to use, which will depend on objective of investigation, resolution required, depth penetration required, physical property to be defined, geometry of dam, and nature of target and host material. There is nothing like one size fit all. A particular tool and technique has to be chosen based on all these parameters.
All right. So now we'll be starting with different techniques which are used for dam investigation. And
In this presentation, I will be covering 5 to 6 different geophysical techniques which are useful for dam. First one is electrical resistivity imaging. Now, application of electrical resistivity imaging for dams include presence of water, moisture, primarily changes conductivity of the dam material, provides vertical section of electrical properties. So it's an excellent method to detect saturated zones. It is also an excellent method to detect leakage paths. Now the basic resistivity method is very simple. It is shown here in the 4 electrode method that if you have 2 electrodes acting as current electrodes and you pump current through these electrodes, a potential will get developed in the ground which can be measured, and this potential is dependent on the current which is flowing and the resistance of the ground which it is offering to the current. So this is a simple principle. So our resistance we know is V upon I. Depending on the geometry of where the electrodes are placed, there is something called geometrical factor, and once we multiply the resistance with the geometrical factor, we get what we call resistivity. Now, resistivity value of different materials are in a particular range. So, for example, we know that if we are talking about unweathered rocks, the resistivities can be very, very high. But as we come towards things like salt water, the resistivity can be very, very small. So that's how there are different resistivity values assigned to different material. Remember, there is a range. And of course, there is an overlapping range. So just by having a single resistivity value, you cannot actually classify a material as X, Y, or Z. Now, the same old electrical resistivity method now has been modernized in terms of electrical resistivity imaging, where we put number of electrodes on the ground. Now, these electrodes can be 64 or even 120 these days. There are systems coming with 120 electrodes. They are all put in a line, connected with a multi-core cable, and now we take readings making 4 electrodes out of these active. So initially, let's say 1, 2, 3, 4 are the active electrodes, so you get resistivity value here, then 2, 3, 4, 5, so resistivity value here, and like this you get resistivity value at a particular depth. Now you increase the spacing, so 1, 3, 5 and 7 become active, so you get value here. So now you get value at this particular level. Like this, by increasing the electrode spacing, we keep getting resistivity of deeper and deeper subsurface. Ultimately, what we get is a 2D resistivity section of the subsurface. So electrodes are here, and once you finish your work, you are able to get a 2D resistivity section showing high resistivities and low resistivities. This is the electrode layout in a normal ground. And once we are working on a dam, electrode layout can be done. For example, on a dam top, we can do a couple of lines on the dam top here on this direction and in this direction. We can do a second line on the dam top. So one is downstream, one is upstream. Similarly, if we have axis in the downstream area, we can do more lines in downstream. So these 2 lines in the downstream here and downstream here. So by doing these parallel lines, actually we will be able to map the zones, the leakage zones properly from one end to the other. Now this is, for example, a typical dam, and This is how we put the electrodes. This is how we can put the electrode inverse on the top of the gallery, and otherwise in the dam body. So once we come in the spillway, obviously we cannot put the electrodes here, so we can do it from bottom up. So this is how small drill holes are made, very small, 6 inches deep, and electrodes are put in the ground like this. It can be done on the paved surfaces, no problems with that. So this is the procedure of data acquisition. Another photograph showing the laying of electrode on an embankment dam. This is small drilling, putting the electrode here, all connected to a multi-core cable. So this is the multi-core cable. These are the electrodes which are in the ground, as you can see. Ultimately, once you do the data acquisition, which takes around 20 to 30 minutes of time, you can quickly process the data, and it will give you a 2D section of the subsurface resistivity values. Now, depending on the kind of formation, we know, for example, this is the resistivity values. We know clay has lesser resistivity values compared to sand and gravel. So like this, you are able to have complete classification of your formation there. This is a beautiful example done from a dam crest. There was a heavy seepage through this dam, and this investigation was done, which clearly brought out these low resistivity zones because of water saturation. Again, a line parallel to that, and now both the zones actually combine as one, and now we can see at what distance these zones are. That is a change of the dam. We also can see at what depth these dams are. So this is basically these zones are. So this is a depth scale, this is a distance scale. Another example from a masonry dam showing the saturation zone very clearly. This is one saturation zone, and this is another low resistivity zone, and this is another low resistivity zone. Again here, a heavily saturated zone, a low resistivity zone here. This is also from a masonry dam. Another example here, low resistivity zone. So the point is simple. The dam material by themselves are insulators. They become conductor only by presence of water and moisture. So once you do a electrical resistivity imaging, you are able to clearly identify which are the zones where there is more water saturation or moisture content, which might be leading to the seepage. Again, low resistivity zones clearly depicted here. Here, number of examples. We have hundreds of case studies of these methods from around the country. This is one example of doing it from inside the gallery roof, and then getting the picture of from gallery roof towards the top of the dam. And these are the normal images. The same results, if we do number of lines, can be actually put into a three-dimensional view. So this is a three-dimensional view of resistivity imaging. This is a block which is 60 meters deep, 60 meter wide, and 300 meter long. And this is all water table. As you can see, this blue is the water table. This was done to find a cavity. This is the cavity. This blue line is the cavity. It was otherwise massive sandstone, but there was one cavity which was suspected here because during the drilling, and this is the cavity which is running from one end to the other. You can see this blue zone is the cavity. You'll be able to see it once we go from top to bottom. So as we cutting it top, this one. So you are able to see these results in the 3D. You are able to visualize them. Then you can cut slices any way you want from this. The next method we are going to talk about is streaming potential. This is again a very interesting method because see, resistivity imaging gives you information about the saturated zones. Now in a dam body there can be multiple saturated zones. Next question is which of these zones is actually contributing to active seepage. That's where streaming potential comes in picture. So this is the potential which develops due to flow. It's a natural potential. It is used for flow path determination. Results are qualitative. So it is always interpreted with other method and mostly with resistivity imaging. So it's like this. When water is flowing through porous medium, it displaces the positive ions which are attached to the material, and that results in a flow of the current. So this is a simple, very simple basic principle of streaming potential. So in case of dam, what happens is that let's say this is the reservoir, this is your dam crest, this is your dam face, and you do number of these SP lines. So this is one line done here, one line done here, one line done here. Wherever the water entry is taken place, you have a negative SP development there. Somewhere in between it will become null, And where you have exit point, that's where you get a positive SP development. It is simply because of ionic movement, as I just explained in the earlier slide. So you see, if you generally observe the seepage here, the natural tendency is that we suspect that it should be coming from a path like this, and we do all the treatment strategy accordingly. But actually the seepage path is like this, and that's why streaming potential is a wonderful method to find out the seepage path. Even when there is stream potential generated by seepage through pond or reservoir flow, if in any particular case there is seepage from the reservoir flow, it can be done from on water also. So once you do it on water, this is the water surface, and let's say this is a zone of flow from which this is a pond floor, water is going inside, you will get a clear SP development around that zone. So this is a wonderful method even to find out seepage through pond or reservoir flow. We use non-polarizable electrode for this, for SP measurement. So this is a non-polarizing electrode. It basically has a copper sulfate solution inside. This is a copper sulfate electrode here, and this is what is used for SP. We keep one station here, and then we keep moving. This is the rover electrode, which we keep moving every 5 meters or 2 meters or 1 meters, depends on what resolution we require. A very simple field procedure is adopted for this, but the results are so useful, which are very clear in this example. This is a dam. It was pretty big, 2.6 kilometers or 2.7 kilometers long masonry dam. There was seepage from this dam, and we wanted to find out which are the zones which have gone weak and which zone is contributing maximum to the seepage. So once we did the electrical resistivity imaging, you can see very clearly this is a low resistivity zone. This also is a low resistivity zone. This is a low resistivity zone, and this is a low resistivity zone. So all these zones have saturation in different amounts. But across this zone, there is a major development of streaming potential. Whereas against these zones, there is no development of streaming potential. What does it mean? It means that maximum seepage is taking place from this particular zone. These zones are also getting saturated. If left unattended, after a few years, they also can become conduit of seepage. And that's why this information becomes so critical that you can do preventive maintenance now and actually take care of these zones before they become conduit of seepage. Lots of examples with SP and ERI. As you can see here, there were 3 zones, 1, 2, and 3, but it becomes very clear that the seepage is maximum across this zone because SP development is very, very profound across this. Next, I am going to cover a ground penetrating radar. It is used for stratigraphic profiles, buried objects. It works on the principle of EM reflections. That is, we send short duration electromagnetic impulses into the ground. They get reflected from any interface across which there is a change in dielectric properties, and it is received back on the receiver. In dams, it is used for characterizing internal structure, finding out soft zone heterogeneities. It can be used as sub-bottom profiler for reservoirs, and it is used for detection of cavities. Now, this is the basic principle. As I said, there are 3 different components. One is the control unit, one is the antenna and the odometer wheel. The signal is sent into the ground. It gets reflected wherever there is a contrast, like an object. It can be a pipe or a cable or a boulder or a bedrock interface. Whenever there is a contrast in dielectric properties, the signal comes back to the receiver and it is finally displayed in the real time on the computer screen. These are a few pictures of data acquisition on dams. This is using a 100 megahertz antenna. This is using a 300 megahertz antenna. This is a dipole antenna with 38 megahertz. There are different frequencies for different resolution and different depth of penetration. I'm not going in detail of these methods, this particular method in terms of principle. Idea is to show you what we can do with these methods. So this is one beautiful example of detection of a cavity using GPR. So this is a cavity structure which was detected using GPR. This is about stratigraphic interfaces. So this is the amplitude anomaly which was found. This is the top of the crest of the dam. So this is distance and this is depth. So these are various stratigraphic interfaces, and there was this zone which gave highly reflective material amplitude anomaly. So this is the zone of what we call anomalous zone in the dam body. This is an example of done on the reservoir. So this is on water, of course. It has been done using a boat. This is again depth 5 meters from here to here. This is top of the water surface. So there is a submerged construction road. You can see boulders, soft sediments, different layers of sediments. So that's how you are able to see, you can have the complete profile, sub-bottom profile under your reservoir flow. It can be done in the cross hole manner. So this is, let's say, one borehole, second borehole, they are 10 meter apart. GPR has been done in the cross hole manner, where you can see this is the area with very, very high volumetric presence of water. So volumetric presence has been calculated based on GPR data. So this is as high as 38% in this particular zone. This is interfaces. So you can see a very clear interface here. This is interface here. This depth in meter. So here we are talking about this interface at around a depth of 2.5 to 3 meters. Another example of dipping shallow bedrock. So this was again taken on a dam. Very, very shallow bedrock was towards one end of the dam body. And this is an example of cavity, and here you see the depth. It is around 12.5 meters of depth, and this is an example of a cavity. The same thing, GPR results also can be turned into a 3D volume. So if you do the work in both the directions, longitudinal and transverse, you are able to make the three-dimensional view of it. So this is the distance axis, this vertical axis is the depth axis, and this is the y-axis, and you are able to find out your anomalous zone inside the dam body in 3 dimension here. And then you can cut time slices. Time slice is like, for example, taking a butter cake and cutting it at one particular point. So this shows at one particular depth. So this is showing, for example, 1.85 meters to 2.15 meters. What is the condition at that particular depth? So you can cut these depth slices at different depth. This also has a wonderful application in Stilling basin, where obviously you cannot empty it, but you want to find out the condition of concrete under it, and it can be successfully used there. We have done it. So this is one case where a small this structure was made to carry our equipment. This GPR antenna was kept in a rubber boat. So this barge was made. This is the antenna. Sorry, and this is the echo sounder to find the depth, and this was a GPR unit. And now you can see the results. So this is the top of the water, and this is 5 meters, the floor of the Stilling basin, very clearly visible here. And you can see this was a deteriorated zone. The client suspected that there has been a lot of erosion and deterioration here because of a flooding incidents, and this was a deterioration zone because you can see this is a very clear concrete floor, but this zone is completely different. There is a deterioration in this zone, and the depth here is around 10 meters. Further, this is a completely eroded zone, deterioration zone here and eroded zone here. And then finally the entire thing was plotted in with the bathymetry data, and this was the area which was worst affected. And results obviously then was transferred into CAD, showing the bathymetry profile, moderately and deteriorated zone, and the GPR profile, and they matches. Both of the profiles match very good, which basically again proves that the GPR readings were very accurate in this particular case. Seismic refraction is one of the most popular methods in engineering geophysics. It is used extensively for determination of bedrock depth, strength of the rock, etc. Before undertaking engineering projects. In dams also it has wonderful applications. It is generally taken from dam top. 2 or more parallel profiles on dam top and downstream side are done. It provides P wave velocity, which in turn gives us the strength of the subsurface material. Now I think you are able to see how we are choosing different methods depending on what exactly we want to determine. For example, we want to look at the level of saturation inside, that will change the conductivity or resistivity. We are going for electrical method. When we are trying to look at the flow paths, we are looking for a method which can detect or which will change with the flow of the water in the porous medium. We are going for streaming potential. We want to see interfaces or buried bodies, etc. We went for ground penetrating radar. Now let's say we want to see the strength of the material. all right, like how hard the material is, or whether there has been any density loss in the material. In that case, getting the p wave velocity will be the great idea, where we will get the strength of the subsurface material. It is used for bedrock mapping, phreatic line determination, seepage zone identification, and of course as post construction QC tool. How it works is that we initiate our energy on the top. It can be done with a simple sledgehammer, 10 kg sledgehammer. Now these rays start traveling whenever there is a contrast in acoustic impedance across, like for example there is a contrast in the velocity at this interface. The ray will go away from the normal. If v2, that is velocity in the second medium, is more than v1, that is in the first medium, is Snell's law. Sin I upon sin r is v1 upon v2. So if v2 is greater than v1, the r is greater than I. At one particular angle of incidence, that's called critical incidence angle, this ray starts going along the second interface, that is r becomes 90 degrees. As per Huygens principle, all the particles on this interface become emitter of the secondary rays, which are then coming here and picked up by these devices on the ground, which are called geophone. Geo is earth and phone is listening, something that listens to the earth. So this geophone records the data which is coming from down here. This is a very simple, very short principle. Ultimately, what we get are again the profiles. This is the depth and this is the distance, which shows us the change in the p wave velocity. Like in electrical imaging, we were seeing the change in the resistivity value. Here we are looking at the change in the p wave velocity. So for example, this is the bedrock interface, and you can see in this particular zone there is an anomaly. Otherwise the bedrock interface goes like this. Again here this is the bedrock interface, and in this area it goes deeper. So it gives a very good two-dimensional or three-dimensional picture of the subsurface. This is how it picks up the phreatic line. So this is based on whenever the water enters unsaturated zone, it becomes saturated and the velocity crosses 14 or 1500 meter per second. This is how the phreatic surface is picked up. This is again an example of phreatic surface being picked up in the dam. So this is the direction of the line, and here the phreatic surface has been picked up very beautifully by seismic refraction. And what is the importance?
One of the most serious dam safety concerns is the stability of the earthen embankment. Unsafe conditions could lead to a major slide that threatens the safety of the dam. A key factor to stability is the location of the phreatic line, or the fully saturated zone of the soils within the embankment. In safe dams, this level is well confined below the surface. Since soils that are fully saturated are not as strong, a higher phreatic line can reduce the ability of the embankment to resist sliding. This is often noted by seepage exiting on the downstream face of the dam. Weak or poorly compacted soils can increase both seepage and the phreatic level, as well as weaken the embankment, contributing to a sliding failure of the dam.
So seismic refraction, as we saw, is a wonderful method to get the p wave velocity. Now in certain cases, we also want to determine the shear wave velocity. In fact, if we have both the p wave and shear wave velocity, we can calculate all the dynamic moduli: Young's modulus, shear modulus, bulk modulus, Poisson's ratio. So REMI and MASW, that is refraction, microtremor, and multi-channel analysis of surface waves. These two methods are widely used to find out the shear wave velocity inside the structure. So it provides the REMI or MASW, it provides S wave velocity of subsurface stiffness, undertaken from dam top, used for earthquake site response, for liquefaction analysis, mapping of subsurface and estimating strength of the embankment, and identification of subsidence zone. This is one of the major area of application, that if we observe certain subsidence from the top, we are able to do MASW quickly and look at the cause and look at these subsidence in deeply. It is based on the principle of Rayleigh wave dispersion. So we create the dispersion curves based on the Rayleigh waves, and based on these dispersion curves we find out what is the shear wave velocity profile of the subsurface. Ultimately the results look like this. So this is a 100 meter depth. This is again an example from a dam which we carried out, and this was the bedrock surface. As you can see, this is the bedrock, and here is a low velocity zone. Ultimately, the masonry from this end to this end is supposed to be of the same quality, but this was the low velocity zone because there have been a lot of seepage across this zone, which has created the low velocity in this zone. Another beautiful example here, this is the bedrock, and this is one low velocity block, this is another low velocity block. So right from the very quick survey, around 2 to 3 hours it took, I think, to carry out this survey, and you're able to clearly bring out the blocks or the zones in the dam which are weak compared to the adjoining blocks. Again, here there is vertical stratification which is normal in terms of construction of the dam, but here is a lateral discontinuity because of the weak zone. And now we are going to discuss the last method for the day, and that's seismic or sonic tomography. Till now, whatever methods we have discussed are done from the surface of the dam, from top of the dam. This is one method which deviates from that. So it provides very high resolution images of dam interior, provides P-wave velocity which is directly linked to strength and density. It is done between two faces. So it can be done between dam top and the gallery. So these are two faces in that case, or can be done between upstream and downstream face. Now with this method the resolution is very high, that you are able to see details very clearly. So it is possible to pinpoint defect zones within the dam. It enables grout quantity estimation. So if you are able to if you do this in a particular dam, you can find out in 3 dimension the extent of your weak zones, and with that you can do a grout quantity estimation. It determines treatment success by pre and post treatment studies. This is just one example, like this is a concrete dam, downstream wall, upstream wall, and seismic tomography has been done, and this is the velocity scale going from 2.1 to 4.4. So anything which is more than this 3.3, 3.4 is good concrete, but anything coming in this range, for example, here you can see the P-wave velocity is very low. So these are the fracture zones within the concrete dam. So the basic principle is similar to what it is done between boreholes. That is, you have once you do it in boreholes, you have transmitter, you have receiver. Now transmitter is sending this impulse, this sonic wave or seismic wave to the receiver. Then transmitter goes to a next depth, next depth, next depth, like this. These ray coverages are there from different levels of transmitter to the same level of receiver. Now the receiver also is changed from its position from top to bottom, and again the same process is repeated. So ultimately the idea is to make a crisscross of these ray paths covering the entire volume of the material being investigated. So how it works is that, let's say there was a low velocity zone here. So we will calculate that how much time it should take for this ray path to go from here to here. But if it is passing through a low velocity zone, obviously it will be curved, it will take a longer time, and that's how this low velocity zone will be determined using this tomography. So you do the inversion once you do this entire process, and after inversion you are able to have a complete picture of your low velocity zones, high velocity zones between the two boreholes. Now in case of dam, the same principle is applied, but we do L section tomography, that is between dam top and gallery. If there are more than one gallery, then we can do between dam top and first gallery, and between first gallery and bottom gallery. Combinations can be endless. Idea is that there should be two faces between which the tomography is to be conducted. Then we do cross face tomography, that is between upstream and downstream phase. So first we'll cover L section tomography. So this is the dam, this is a gallery. So this is where we keep our transmitter or short points on the dam top, and the spillway crest. So this is where the spillway crest, we keep our short points here. So this is how it is. Dam top, we are doing the marking. It can be every 1 meter, 2 meter, 5 meter, depending on the resolution we are looking at. And this person is creating a shock wave here by a sledgehammer on the dam top. And this is the same thing which is done on the spillway. So this is this particular line. This is where it is being done on the spillway. And receivers are kept here. in the gallery. So on the gallery roof, the receivers are kept. So this is, you can see, receivers, that is geophones on the gallery roof, geophones on the gallery roof. So now here is our source and here is our receiver. So we'll just take a small section just to visualize how this whole thing is happening. So we've just taken one part of the entire gallery. So here we have put our receivers. They can be 24 or 48 receivers at one time. We start our first shot, and these rays travel from shot point to all the geophones. And then we change the position of the shot point, go to the next shot point, same travel of ray paths from that shot point, next. And like this, extensive coverage of the entire dam material is done from different directions. So again, we go to the next shot point. So now you see the rays are crisscrossing the dam material in every possible way. And this crisscrossing basically determines with what resolution you will be able to get the data of the dam interior. So this is the kind of crisscrossing that has happened. So after this, the entire volume is actually divided into unit cube volume. And then there is a T observed and there is a T calculated. And based on that inversion, we find out the velocity of each unit volume of the dam material. So this is how in the real world, this is a ray path coverage. This is the example of a dam we have done in India only. And you can see these are all shot points on the top. The distance from here to here is around 400 meters. And this is the gallery, and these are the position of the receivers. So this is the extensive ray path coverage that is done. And then inversion is carried out. And once the inversion is over, you get a beautiful P wave velocity distribution of the dam interior. Wherever you have these low velocities, these are the areas where a lot of material has leached out because of seepage. And of course, once you do the treatment, you will need to focus on these areas. So very, very clear picture of entire dam length, where exactly the problem areas are. Now, once you have found these kind of problem areas, you can ultimately do cross sections. That is, this was the L section. Based on this, you know that this is one area, this is one area, this is one area where I have weak zones. So you do not need to drill through your entire dam to find out where the weak area is. A simple, like this entire L section, I think took around 1 day or 1.5 days of time, and you have the entire internal image of your dam body where the weak portions are. And once you do that, then we come to cross phase tomography. So cross phase is between the upstream phase and the downstream phase at the location which you have seen in the L section are weak. So in cross phase tomography, we divide it into two parts. One is the above water area. So this is your reservoir level. This much area is above water. So you can put receivers on the upstream side and transmitters or short points on the downstream side. So these are the receivers on the upstream. You can see these are the receivers on the upstream, and this person is going down and he will be hammering at different point almost every 1 meter along the downstream. So these are the receivers, and this is the first shot point. This is a simple small hammer, 2 kg hammer. He strikes with that, waves travel all the way. Next point, again waves travel all the way to all the receivers. This is continued from one end to the other, and again the idea is to have extensive crisscrossing of these waves like this. So once you have this extensive crisscrossing, means you will get a very high resolution image of each unit volume inside this area. Now once we come to underwater, this particular position, there are two options. One is that we can have receivers or hydrophones in this area, or the second is that we can have transmitter or sparker in this side. If we have receivers in this area, we'll have to have transmitters here. If we have transmitter in this area, we'll have to have receivers here. I'll show you both the options. So this is option one, hydrophone strings. Hydrophone is just like geophone is listening to earth. Hydrophone again listens to the small seismic signal but inside the water. So this is the hydrophone string, and now hammer will be on this side. So this is the hammer, this is the hammer, this is the hammer, this is the hammer, this is the hammer. Like this, at different points, this hammering will be done, ultimately to have a crisscross of ray paths in this area. A second option, if you have receivers on this side, you can have your sparker. Sparker is a device. This is a sparker picture, which again produces seismic waves inside the water. So you start the seismic waves inside the water, again take the sparker to the next step, next step, next step, and like this to the bottom. Ultimately, to have this kind of ray coverage between the upstream and the downstream phase. And again, we go for inversion. And once the inversion is over, you have a detailed p-wave velocity distribution inside the dam. So now you know very clearly upstream to downstream which is the area which is having low p-wave velocity. So this is the defective area. Now you really don't need to, for example, go for blind grouting from top to bottom, etc. You know exactly which is the area and what is the dimension of the area which requires treatment. So this is a very high resolution technique which can be beautifully used for masonry and concrete dams. So this is how the results look like. This was the L section. Based on the L section, cross sections were planned depending on where the anomalies were found. And now these cross sections will give you exactly uh, the extent of the area in this direction. So this is your horizontal direction and this is the transverse direction. So practically you have a 3D image of the entire dam body. Now this is a velocity tomography. So this is a case study from my spillway. So you get velocity. Now here the velocities are low, so obviously this is the area of defect. These are the normal velocities what they are supposed to be in the masonry. And now this p-wave velocity tomogram can be converted into density tomogram using Gardner equation. So now you know that this is the normal density which is more than 2.45 or 2.5, and here is the area where the density is as low as 1.8 or 1.9, and so you know exactly what is the deficiency in terms of density. Now once you have this figure, this helps you determine the grouting quantity. Another example of the shoulder. So here this was the low velocity zone converted into density tomogram, and again you can see very clearly what is the low density zone inside the dam. So this was about seismic tomography. So I think we have been able to cover the methods starting from the one which are done from the dam top, going to a very high resolution method of seismic refraction, seismic tomography, cross face and L section tomography, which gives you a very detailed information of the dam interior. So the next question is, when do you need to investigate your dam? Now, it is actually desirable to have a baseline data of dam soon after completion of dam. Fact is that as we grow old as human beings, like if you go to a cardiologist, he says that you should get a baseline ECG done, because then in future I can keep comparing your ECG with this baseline ECG. Similarly, in case of dam, even immediately after construction, we should be able to have a baseline data so that we know what is the condition of a freshly constructed dam. Now, in case it has not been done, obviously in case of older dams, this time is now, because we could not collect this data at that time. The technology was not available or awareness was not there, but then it should be done as soon as possible. So the time is now. Before designing a rehabilitation program, it's almost a must. Because how can you design a good rehabilitation program without knowing where exactly are your weak zones, what is the extent of these weak zones, what is the density deficiency that has taken place? So it has to be done before a rehabilitation plan is designed. Then after carrying out rehabilitation work, you have done the rehabilitation work. Now, how do you know that the grout actually has gone to the zones which you targeted? So to check the efficacy, it must be repeated after rehabilitation. Now, the most important thing is that changes in physical properties are much easier to interpret than one-time measurement values. What it basically means is that, as we said earlier, that if we talk about resistivity or density or any of these physical property, just taking a one-time value and trying to interpret it, it's not that easy. For the simple reason that there was a whole range of these values for different materials. But if you take the value today and then you take a value after 2 years, comparison is much easier, and it will tell you how things has changed over a period of time. Now, under normal conditions, such measurements should be repeated every couple of years as a routine dam inspection program. As of now, as we saw, dam inspection program is mostly inspector dependent. A person goes there, looks at the dam, etc. Depends so much on his skill and his motivation level. So ideally for the dam, this should become a routine inspection protocol. So to conclude, I would like to say that this is the most suitable method for regular health check of dams. It is used for early detection of problems. It's totally non-destructive, so extremely suitable for a structure like dams. It helps design rehabilitation programs better and accurately. It helps assess success of rehabilitation measures which have been undertaken. It's for identification of damaged areas inside the body of the dam, identification of not visible fractures and voids, and identification of zones of seepage. So more information at low cost and very quickly.
We have looked at various techniques very quickly in as short a time as possible, almost 1 hour. Now, my question is, you want to learn more about these techniques? So if you want to learn more about these techniques, we have an opportunity for you. And the opportunity is that we at AF Academy is going to conduct a 3-month course on dam geophysics. And course components, as you can see, are leak path detection, internal erosion, identification of zones of water accumulation, cavity, sinkhole, concrete masonry degradation, residual density determination, sitting basing application. All these will be covered. And geophysical techniques we are going to cover are going to be seismic tomography, electrical resistivity imaging, multi-channel analysis of surface waves, seismic diffraction tomography, streaming potential, and GPR. Practically all the methods which I have discussed in very, very brief today will be discussed and given to you in much detailed manner with all the field data acquisition procedures, the processing procedures, the software involved, etc. Now, how we are going to do is that we are going to have a live webinar every 15 days to deliver the course, and minimum 6 webinars will be conducted, just like what we are conducting today with Q&A session. Training modules. A lot of reading material has been prepared by us on these aspects that will be given to you. You'll also become member of a members only Facebook group to interact with the group members on various aspects of dam geophysics. Email and online support will be available where you can write to us at any point of time for any dam related problem. And at the end of this program, you will get a certificate from AF Academy that you have completed a program successfully on geophysical investigation of dams. Other available courses with AF Academy in the same mode are 3 months course on GPR, certificate course on SUV, and another self-learning course on SUV, which you can opt for. And these are the contact details. For any course-related query or payment gateway linked assistance, you can contact Mr. Rashik. His email ID is here. For any requirement of dam geophysics or any other geophysical services, you can contact Commander Ashutosh Kaushik. He is CEO of Parson Overseas Private Limited. His email ID is given on your screen. And for any technical clarification, you're free to contact me. My email ID is also given here. And all these email IDs will also be sent to you by the mail after this presentation.